This episode is supported by Squarespace.
Meet Starship, the largest and most powerful spacecraft ever attempted. Skipping over all of the incremental milestones that will come before, SpaceX's long-term goal for Starship is to enable them to send 1 million humans to Mars by the year 2050. I know, right? Sounds like a pretty tall order. To accomplish this, Starship will not only have to be 100% reusable, but it must be rapidly reusable. In this case, the word rapid means we should eventually expect to see multiple launches in a single day from the same launch pad. For this reason, the vehicle, and more importantly the launch system, will need to be extremely robust. But what does a robust launch system even look like? Well, for one, it won't be partially destroyed every time the Super Heavy booster ignites more than 10 of its Raptor 2 engines. Following both of the last two static fire attempts, we have seen SpaceX replace the concrete pad underneath the launch mount, even after upgrading it to a higher strength, explosion-resistant concrete blend. Each time, this required 2 weeks of work to make the necessary repairs. As expected, this has fueled more debate by fans and critics alike that SpaceX seriously needs a flame trench underneath the launch mount. It's pretty clear that SpaceX does not have plans to do this, though. And in reality, it's not really possible without a complete redesign of Stage 0. So, should we really expect SpaceX to continue spending 2 weeks replacing the concrete in between every static fire and launch? Or is there something that we all missed? My name is Zach Golden, and welcome to another CSI Starbase Special Report. Hey Starship addicts, thank you for joining me for today's special report. There's been a lot of hype lately about whether or not this concrete pad underneath the launch mount might be the Achilles heel that will prevent Starship from ever achieving rapid reusability. For example, let's take a look at what Marcus House from the Marcus House Show had to say about it.
I mean, we know that the ultimate goal by SpaceX with Starship is to create this fully reusable rocket. At the rate this is currently going though, maybe SpaceX should instead be setting up an expendable pad production line. I'm joking of course, but yes, it does seem like this will remain a continual problem until a new solution is found.
Marcus took this joke even further and released this special edition t-shirt depicting concrete being vaporized underneath the Orbital Launch Mount. Let it be known that he was not alone in this way of thinking. Trust me, I was guilty of it as well. I even went so far as to start factoring in 2 weeks for orbital launch pad repairs into my calculations when trying to predict the most likely date of the first orbital flight test. 4 weeks if they decided to perform a 20-something engine static fire test before they jump up to firing all 33 at the same time. As you can tell by the title, I have since reversed my opinion on account of a simple yet important piece of evidence that I discovered last week. In order for any of this to make sense, I'll need to start by giving you all a little background information so we're all on the same page about why this is even relevant in the first place. It all started the day after the 14-engine static fire test on November 14th of 2022. As of the time of recording this episode, this is the most engines we have ever seen tested on the Super Heavy booster. During this test, we witnessed something that I think we can all agree was truly terrifying, yet absolutely spectacular to watch all at the same time. After the moment of ignition of the 14 Raptor engines, LabPadre's Rover 2 cam was shaken so hard that it caused the camera to pitch forward so it was pointed at the ground instead of at the launch mount. Initially, this was a bit disappointing. However, it forced us to focus our attention on the brief hailstorm of hot concrete as it began to precipitate into the street. There were some questions as to whether or not this was debris from around the launch pad or if it was truly coming from directly underneath it. Thanks to LabPadre's Predator camera, we were able to see the temperature of the rocks as they came to rest in the street after traveling several hundred feet through the air. This pretty much eliminated any remaining doubt as to where this material originated from. Unfortunately, due to poor weather that persisted in the area for 2 weeks straight, Mauricio from RGV Aerial Photography wasn't able to perform a flyover in time for us to get a bird's eye view of the damage. From the ground, we were able to identify a single deep crater in the concrete. However, it was difficult to see much else because there was so much heavy machinery equipment underneath the table. What Mauricio did find, however, was several pallets with white bags on top of them, which had a label from the manufacturer with the name Fondag RS in big letters. Those of you who follow CSI Starbase on Twitter or watch the RGV Aerial Starbase weekly livestream from that week may already be familiar with this. Reading from the Fondag RS datasheet, we can see that inside of these 3,200-pound bags is a specialized, high-strength concrete designed for use in industrial applications that may require refractory performance. The word refractory refers to the material's ability to resist decomposition by heat, pressure, or chemical attack. This substance in particular is meant to withstand exposure to temperatures up to 2,000 degrees Fahrenheit or about 1,100 degrees Celsius. It also has a compressive strength of more than 7,500 psi. So knowing this, let's do a little math to determine whether or not we should expect this material to survive the abusive smackdown that will be handed down by the Super Heavy Booster's 33 Raptor engines. Let's start with the compressive strength first because that's the easiest to explain. I'm going to simplify this by only considering a single engine here. According to SpaceX, the diameter of the exit of the Raptor 2 engine is 51.4 inches, which gives us an area of 2,075 square inches. Now, let's make a few assumptions here. First, let's say that 100% of the thrust generated by this engine is applied directly to the ground. Let's also assume that the area this force is being applied to is a circle of the same radius as the nozzle exit. To all of you engineers out there, the reason I'm making these assumptions is to provide an overestimate for the destructive potential of these engines. In reality, the plume will spread over a larger radius, and the force exerted on the ground will be significantly diminished. Raptor 2 engines are known to produce at least 510,000 pounds of thrust. Dividing that by the area of the circle gives us 245 pounds per square inch. This is well below the 7,500 psi that this concrete is rated for. By my calculations, this Fondag RS should be able to withstand up to 30 Raptor engines all pointing down at that same 51-inch circle at the same time. Okay, so now that we know that the Fondag RS is more than strong enough to withstand the compressive force of the exhaust flow, let's talk about its resistance to thermal energy. The reason thermal energy is an important consideration is because of the tendency for concrete to explode if it's heated up beyond a certain point. This phenomenon is called spalling. The reason it happens is because even after it's cured, there is still residual moisture trapped within the concrete. If the concrete is exposed to temperatures exceeding 212 degrees Fahrenheit, which is the boiling point of water, the moisture in the concrete will turn into steam. The formation of steam will cause pressure to build up inside of the pores of the material, and without anywhere for the steam to escape to, the pressure will exceed the strength of the concrete and cause fragments to break off in an explosive manner. You can see evidence of this all over the base of the Orbital Launch Integration Tower. It's important to note that the more heat you apply, the more severe the spalling damage will be, especially if it's over a large area. So we need to know what kind of temperature to expect on the surface of the pad underneath the launch mount. Again, we're going to simplify this down to a single engine. It was difficult to find the temperature data for the Raptor exhaust plume, but luckily one of our agents, codenamed Oscar the Grouch, was able to locate some information in Appendix G of the FAA's Program Environmental Analysis Report. The purpose of this section of the report was to estimate the far-field exhaust constituents of the SpaceX Raptor 2 Methalox booster rocket engine firing under sea level conditions. Essentially, this was an emissions test, which conveniently included a table showing the predicted exhaust plume temperatures at different distances below the exit of the nozzle. We can ignore the green, blue, and yellow lines and just focus on the red one. From this data, we can see that as the exhaust leaves the nozzle, the temperature of the plume will be around 3,500 Rankine, which is equal to about 3,040 degrees Fahrenheit. That's pretty hot, and it's actually on par with the temperature from the exhaust of the Space Shuttle solid rocket boosters, which are also used on the Space Launch System. Now, in order to determine the expected temperature on the surface of the concrete, we need to know the height of the bottom of the engine bells. Thanks to Ryan Hansen Space, we can say that this is roughly 16.5 meters or 54 feet above the pad. So according to this chart showing the drop-off in temperature as a function of distance, at 54 feet, we should expect the exhaust plume to have cooled to about 800 Rankine, and that's 340 degrees Fahrenheit or 170 degrees Celsius. Not as hot as you might expect, However, this is still hot enough to cause the spalling effect in regular concrete, which is something we have clearly seen on each of the static fire attempts so far. This datasheet does not provide information for what to expect during a 33-engine static fire test, however, and that is important to note. During a single-engine test, the exhaust plume is surrounded by ambient air. The exhaust flow will mix with the ambient air along the boundary layer, which is called air entrainment. This rapid air entrainment is what causes the drop in temperature downrange. When all 33 engines are firing, the dynamic of this situation changes completely. Let's consider the outer 20 engines first. Looking at this from below, you can see that on what SpaceX refers to as the outbound side, the exhaust flow will experience entrainment with the ambient air. To some degree, it will also be affected by the Firex and detonation suppressant system, although that feature of the launch mount is not given consideration in this report. On the inbound side, there are 13 center engines firing at the same time as the outer 20, so instead of mixing with ambient air, it will actually experience exhaust entrainment. This exhaust entrainment also happens on the sides facing the two adjacent engines on the outer ring. According to the report, this is approximately 50% exhaust entrainment for the outer 20 engines, but for the center 13, it's 100% exhaust entrainment. There is no ambient air inside of this column of fire to help with the cooling of the exhaust flow. So in the center of the pad is most definitely where the highest temperatures will be found, although we don't know the exact value to expect. So 340 degrees is our low-end estimate, and as long as it doesn't exceed 2000 degrees towards the center of the pad, then this Fondag RS should do the job. Keyword should. I know that some of you will want to review this information for yourselves, so I will include a link to it in the description. In future investigations, I plan to gather all relevant supplementary research and evidence material and store it all in one place so you can review it on your own. I've been meaning to do this for a while, but back in my day, creating a website involved a whole lot of tedious HTML coding. Ain't nobody got time for that. Luckily, those days are history. And thanks to Squarespace, who is the sponsor of today's CSI Starbase special report, creating our digital evidence locker will be easier than ever. If you are someone who is looking to create your own website, Squarespace is a one-stop shop for purchasing your own domain name and then designing your page using their massive selection of custom templates. Once you've chosen a format that fits the style you're looking for, you can quickly customize it using their drag and drop block editor to give it a unique look. One of my favorite features about Squarespace is their extensive library of stock images that you can search through to create amazing backgrounds like this one. Well, 99% of their images are top-notch, but this one is clearly a fake. So I think I'm gonna go ahead and swap that out for one of my own. And there we go, that's more like it. If you've been thinking about creating your own webpage, then stop procrastinating and head over to squarespace.com/CSI Starbase and save 10% on your first purchase of a website or domain. All right, so continuing where we left off, we now know that Fondag RS should be more than capable of surviving the brutality of the Super Heavy Booster's 33 Raptor 2 engines. On November 27th, Mauricio took this photo of the freshly placed pad under the launch mount. From our understanding, this was taken the same day that the Fondag was laid. You can even see the power trowel still down there applying the finishing touches to the pad. Less than 48 hours later, on November 29th, after giving it the absolute minimal time to set and cure, SpaceX performed an 11-engine static fire test. There were less engines tested here than in the previous one, however, it was for a longer duration because SpaceX wanted to test the autogenous pressurization system on Booster 7. At first, we thought the new pad held up pretty well. It appeared there was less debris this time, but that was until we checked Epic Spaceflight's hoop cam and realized that the same concrete hailstorm occurred yet again. Apparently, the wind was blowing more to the north this time. The amount of shrapnel seen falling from the air was significant, but it wasn't as bad as the previous test. Looking at the aftermath from the air, we can see multiple craters in the ground. The craters were so deep that you could see the self-propelled modular transports had to struggle to pass over them the next day when SpaceX went to remove a few of Booster 7's Raptor 2 engines. Once the engines were removed and Booster 7 was out of the way, SpaceX began breaking up the pad for a second time on December 7th, while Starship Gazer was on site to record the action. This time around, we were able to get an aerial view as they began preparing the foundation for laying more Fondag underneath the launch mount. I think when these images came out, a lot of people were confused about what was going on here, and there was speculation about a possible flame diverter being installed under here, but what you're seeing here is just wooden framework laid out in a pattern. This pad is very large, so it must be laid out in sections instead of doing the whole thing at one time. Once the area that's enclosed in formwork are completed, the forms are removed and then the edges of the concrete become the forms for the remaining sections. Nothing really special going on here. So over the next week, SpaceX used the Fondag RS to reform the pad. The bags had been temporarily moved near the suborbital side of the launch complex to get them out of the way during the previous static fire. SpaceX brought in an empty mixer truck for the special job. It was a difficult one too because the wind was clearly not cooperating as they tried to empty the 3,000-pound bags into the hopper. Anyways, when it was all said and done, this is what it looked like. The full process took 2 weeks from start to finish. So here's the question that's still on everyone's mind. Is SpaceX going to have to spend 2 weeks repairing the pad after every static fire that involves more than 10 engines and after every launch? If such a major part of the orbital launch pad is essentially expendable, don't we have ourselves a major problem here? Well, here's where the plot twist comes in. I think that we all need to chill out and give SpaceX another chance to prove that this really isn't an issue like we think it is. And here's why. These bags were originally delivered before the first time the pad was replaced on November 18th. It's hard to tell from this angle, but there were exactly 13 bags of Fondag RS on the ground in this image. We can match this up with the aerial view that was taken by Mauricio a week later on November 27th after the job was completed. So these are the same 13 bags that were originally delivered. The bags were moved over near the suborbital pad during the static fire test. I think the disappearance may have fooled a lot of folks, myself included, that this Fondag had actually been used, but in reality, it wasn't. I think the fact that SpaceX performed the static fire within 48 hours of completing that first job probably should have been a big hint of what was going on. Reevaluating the situation, I think that SpaceX was preparing to install the Fondag RS after the 14-engine static fire, but they decided that they wanted to get the autogenous pressurization test completed as quickly as possible before they sent the booster back to the Megabay for its final upgrades. In other words, this was a brand new concrete pad that was intentionally sacrificed. The booster actually did SpaceX a favor by removing a lot of the material for them so that they didn't have to do as much work to rip it out when the time came. I think that during the upcoming static fire tests, we will see much better performance out of this pad, and hopefully, it won't have to be replaced again for a very long time. If I'm wrong about this, I welcome you all to search me out on Twitter and send all of the hate mail you can muster. I may not always reply to DMs, but I do try to read all of them, which is how I knew that a large portion of you were concerned with this situation in the first place. Okay, so I think there's one important disclaimer to add here. While I don't believe we will see the pad directly underneath the launch mount sustain the same damage that we have seen in these past tests, the same cannot be said for the surrounding concrete. From the aerial view, you can see that on the perimeter of the legs of the launch mount, there is regular Portland cement outside of the Fondag pad in the center. This concrete will continue to experience constant degradation over time as engines are tested on the launch mount. This means that there will still be a significant amount of high-speed projectiles dispersed in all directions, which can result in damage to the ground support equipment inside of the orbital tank farm. This is why SpaceX has added an additional ramp to the top of the berm with a steeper angle that should direct the plume of the Raptor exhaust over the tank farm instead of through it. Fingers crossed on that one though. In front of the berm, SpaceX has also added a large step to what was originally just a continuous ramp from the bottom to the top. I think that the purpose of this step is to prevent debris from rolling across the ground and then being launched over the ramp. The placement of this nearly 10-foot tall step will cause the ground debris to collect along the wall or be pushed to the left where most of it will wind up on the pad, or to the right where it will land inside of their designated collection basin. The wall has a secondary function to protect the pipe that is encased inside of it. This is the detank drain for the 2 cryo testing stations next to the berm. Anyways, I know that even though I have recommended that we all be patient and wait to see what happens during the 33-engine static fire and launch, there will inevitably be comments to this video that mention the need for a real water deluge system. If you are one of those people, then I have some good news for you. This is pure speculation, but I believe that SpaceX is planning to add in a water deluge system to this launch mount sometime after the first or second orbital flight test. A few weeks ago, we noticed that several unremarkable-looking sections of black pipe had been delivered to the Massey's test site, located a few miles from the Starbase facility. What we can see here are 2 black T's that look like this, and 4 curved elbow sections of pipe. Looking at some of the surrounding material on the ground, we can estimate that these pipes have a diameter of about 4 feet. Located just a few feet away from these pipes are 3 large valves, which are clearly meant for water, given that they are short-stemmed valve actuators. If these were for cryogenic fluids, the valve stems would be much longer, similar to these ones. I am convinced that this is the beginning of a water deluge ring for the Orbital Launch Mount. If so, it will look very similar to the one installed around the second launch mount at Pad 39A a few months ago. Thanks to this render from Benedikt 3D, you can see what this massive water deluge ring looks like. It has 6 corner pipe sections and 2 T's located on one side, which serve as inlets for the water supply. The only thing missing is 2 more corners and the 6 straight sections that connect them. Although I think we may have found those as well. We located these 6 pipes delivered to the Sanchez site last week. You can see that one of the T sections had been moved over here as well, which suggests we might see construction of this large manifold begin within the next few weeks. Once complete, it will be buried underground around the perimeter of the launch mount. Unfortunately, there's already a large amount of pipes in the ground surrounding the OLM, so there's a good chance that this deluge ring will have to be constructed in sections instead of lifting the entire assembly in at one time. The next question we have to ask ourselves is, where will the water supply come from? There are 2 options here, and one of them is a little more difficult to pull off than the other. The first option is using the 2 existing water tanks at the Orbital Tank Farm. These were converted over from being methane tanks last year after the original water tank was damaged. If you haven't heard the story about why this took place, then I recommend checking out this deep dive investigation I released explaining why the first tank had to be abandoned. So, even though these have been converted to water tanks, the existing water supply that taps into these is way too small to supply the amount of water required by this deluge system. These black pipes on the ground are about 19 inches in diameter, versus 48 inches in diameter for the water deluge pipe. Over the last few months, I have noticed that SpaceX has been adding in additional pipe racks that seem to be running towards the discharge side of the water tanks. It's possible that we could see significantly larger pipes added here to supply the water deluge system. Or we may even see the previously damaged water tank be put back into service. Another option would be constructing an additional water tower somewhere closer to the launch mount that would require a lot less work to route the pipes over to the structure. It would be really difficult to run pipes underground from this location. The most ideal location I can find for installing a new water tank would be on top of this raised square behind the integration tower. The placement of this pad is very familiar if we look at the new launch tower being constructed at Pad 39A. Located in the shadow behind the OLIT is a raised storage tank. I'm still not convinced that this is a liquid oxygen storage tank as everyone else believes. I still think there is a possibility that this is in fact a giant water tank. The main reason for assuming that this is not a water tank is because it is double-walled like the cryogenic storage tanks at Starbase. The void space between these tanks is filled with expanded perlite for thermal insulation, and there should be no need to insulate a water tank. There are a few key differences between the tanks at Starbase and the one that we are seeing here. For one, the inner storage tanks inside of the cryoshells at the Starbase tank farm were constructed with rounded domes at the bottom, whereas the one at Pad 39A is actually just a flat bottom tank. This actually makes it more similar to the original water tank at Starbase. For this tank, SpaceX welded steel plates together to form a flat circular base. The water tank was placed on top of this and bolted to the ground. Returning to Pad 39A, the interior storage tank here was constructed the same way, with a flat bottom, which seems to be an irregular method of constructing a cryogenic storage vessel. The second difference to note is the elevation of the tanks. Raising the height of the locked storage tanks so that it's 15 meters or so higher than the ones at Starbase doesn't really make a lot of sense. It's definitely an advantage when it comes to providing head pressure for LOX pumps that are used to fill the booster in Starship, but the pumps at Starbase seem to do just fine with the tanks mounted lower to the ground. Can't really say the same for the pumps on the methane side, but that's a completely different story. The increased elevation of this tank is one reason our team is still on the fence about this being a water tank. Having it raised this far off the ground could make it useful for a gravity-fed water deluge system. Now, this is nowhere near as tall as the water tower used for the Falcon 9 water deluge system, but this is where the double-walled tank comes into play. In order to move water at the rate needed for a deluge system, you need a pretty decent amount of hydrostatic pressure. As an example, the Falcon 9 water tower is more than 290 feet tall. At this height, the hydrostatic pressure would be 125 psi or 8.6 bar. The large double-walled tank is raised about 50 feet off the ground. This gives us 21.65 psi or 1.5 bar. This is a difference of roughly 100 psi or 7 bar of static pressure between the outlets of these two tanks. One possible option to make up the difference is to use vaporized nitrogen to pressurize the water tank and force the fluid out at the same pressure that it would be if the tank was mounted 240 feet higher. The problem is, 7 bar may actually be pushing the limits of what the tank is designed to hold. One way around this would be to pressurize the void space in between the shell and the storage tank. By doing this, you can generate an opposing force to the 7 bar of pressure being exerted on the wall of the tank from the inside. So if you pressurize the void space up to 5 bar, then there will be 5 bar pushing in on the outer wall of the water tank, which counteracts the 7 bar that's pushing out. This means that the net force being experienced on the walls of the tank would be reduced down to 2 bar. As the water is draining, more gas will need to be pumped in to replace the volume and maintain pressure. This would explain why there is a pipe going into the top of the interior storage tank. This could be used for injecting nitrogen to regulate pressure. The key is to make sure that neither tank exceeds its designed load rating. I would go deeper into this, but I'll just leave it there for now. Anyways, whether SpaceX decides to use their existing water tanks or construct an entirely new one, they're going to need to run a lot of pipe in order to get it from point A to point B. If you've been watching NASASpaceflight's Space Coast livestream, this week you may have seen tons of equipment as it was being moved to the turn basin at the Kennedy Space Center complex. This is clearly part of the Water Deluge System and is made of some pretty interesting looking pipe manifolds. In particular, the ones that have gotten the most attention over the last week were these ones shown here. The most interesting part of this manifold is not what it's used for, but where it came from. What you are looking at here is the original Water Deluge System for the BFR flame trench. That's right, the original purpose of this manifold and pipes were to supply water to what was originally planned to be the test stand / launch pad for the BFR rocket. The stand used to sit right here in this location, but was demolished in 2021. The only thing remaining from it is this water system. This is what the stand looked like while it was being constructed. You can see the water pipes running underneath the bottom of the frame just behind the flame diverter. I'm kind of glad this was never completed because the concept drawings of what it was supposed to look like were interesting to say the least. Anyways, you can see here that the main water supply actually comes from the same source as the Falcon 9 water deluge. Once the 4-foot supply line reaches this location, you can see the smaller pipes that branch off from the manifold and reach over to the equivalent manifold on the other side. Half of these branches appear to be about 12 to 18 inches in diameter, while the other half are about 18 to 24 inches. It's a bit difficult to judge. Attached in the middle of the two manifolds joining them together will be 7 valves. These valves can be either open or closed. There is no partial opening of these valves apparently. This means that the flow rate is determined by how many of the valves are opened. This is very similar to the valves found on NASA's Pad 39B Deluge System, which you can see at the bottom of the tower in this image. The main supply breaks off into smaller branches and then rejoins into 2 separate large diameter pipes that then run all the way up to the deluge nozzles on the pad. The cool thing about this system is that if you watch the water deluge in action, you can actually see an immediate change in the flow rate every time another one of the valves open. I didn't explain how many valves are used for the flow rate settings on the Pad 39B Deluge System because I'm hoping that some of you might be able to count them just by looking at this footage a few times and then letting me know your answer in the comments. There is one final component of this deluge system to mention, and I saved it for last because I'm not entirely sure of its purpose. If you take a look at these 4 horizontal storage tanks that were also loaded onto the Marmac 2680 barge for transport to Starbase, you will see that these are the same ones that were originally located near the valve manifold. All 4 of these tanks were connected together on the bottom using this straight manifold shown here with 4 points on one side. I will have to study this more, but I believe these may be intended to function as a buffer tank that would reduce the effect of water hammer in the lines once the valves are slammed shut. It's difficult to know for sure because construction was never completed on this system. So with that said, we'll just have to wait and keep our eyes out to see how this is implemented at Starbase. Again, this may be a bit of a stretch based on minimal available evidence, but let me know what y'all think in the comments. If you want to hear about this topic as it's developing, then don't forget to tune in to the RGV Aerial Starbase weekly live streams every Saturday at noon Central Time, where we spend 3 hours covering all of the latest updates of Starbase. If you enjoyed this episode, then do us a favor and let us know by hitting that like button and subscribing to the channel if you haven't already. We have lots of awesome content just around the corner, including an incredibly thorough deep dive into the history of Starship qualification testing. I've been asked a lot whether or not I plan to be in Starbase for the first orbital flight test, and the answer to that is yes. I wouldn't miss this for the world. If anything goes down, I want to make sure that I'm able to provide a first-hand account for all of you. In order to properly cover this experience, I will be upgrading a lot of my equipment before heading down there. We recently purchased a new Sony FX30 with the help of some generous viewers who have made donations toward our ongoing camera fund. I want to thank everyone who has helped us to reach this point. Unfortunately, the 10mm lens that I use for recording these scenes will not be very useful with covering a launch like this from several miles away. So we will be investing in 2 telephoto lenses that will help maximize the experience we are able to share with you all while we're there. If you would like to help us to upgrade our equipment in time for the big event, you can do so by donating via the PayPal link in the description. Every donation made via PayPal goes straight to the equipment upgrades. If you would like to support us in other ways, you can do so by becoming a member of the YouTube channel by hitting the join button, or you can become a monthly supporter on Patreon. Those of you who support us on these platforms are directly helping us to continue to make these shorter special report episodes in between the longer deep dive investigations, which take a much longer time to put together. Before I get out of here, I want to say a huge thank you to all of the photographers whose content was featured in this investigation, and to the 3D forensics agent Benedikt 3D for quickly providing us with the render for the Water Deluge manifold in order to allow us to help you all visualize that better. Make sure you follow him on Twitter for even more great content. Last but not least, thanks again to Squarespace for their generosity in sponsoring this CSI Starbase special report. With that, my time is up for now, so I'll see you all next time. Stay Zero Zach, signing out.